This is Mario with MIA Microflight, and in this video I'm going to be talking about tube benders. And this is tube bending at quarter scale, meaning that the tubes that I'm going to be bending are quarter inch in the outside diameter, aluminum tubing. These have, I believe these are 1/32 wall, 0.031 of an inch in wall diameter, or wall thickness rather. And this is to basically mimic at quarter scale a bender which would be about 1 inch tubing in outside diameter. The other reason why I decided to do this is because I have had benders in the past that I kind of quickly did to bend tubing, but I wanted something with precision so that I can start bending a miniature go-kart at quarter scale. And particularly the one that I'm working on is an Alley Cat, an old vintage go-kart. The Alley Cat was popular back in the 60s or 70s, I believe. And so I decided to make a quarter scale model of that just so that I can get just the right proportions and angles before I build the real one, the full scale one. So I had to design basically a tube bender that is also going to work at full scale with a similar parts and process. So this is about tube bending at quarter scale. As you can see here, there are a number of pieces that I've already done. Most of these are 3D printed. All these pieces that you see here are all 3D printed parts, and I'm just using PLA for the time being. But I started with something like this that had the wheel, the bending wheel, and of course this wheel is not at the diameter of the full scale one, which is this one right here in scale. I mean, because the benders, the dies for the 1 inch pipe in full scale, they're about 3 inches in radius or 6 inch in outside diameter of the die itself. And this actually came out at quarter scale a little bit bigger, but it gave me an idea on how I was going to do this and have this dial here where it has all the angle settings, so I could just adjust this and just use this as my carrier, so to bend this. And this also had another piece here that broke, and so it was kind of similar to what I have here. This bender, I'll talk about this one because this is my latest one. Kind of similar idea here, but it had this large wheel. So that was my first one that I did. And then I went on to making this black one right here, which had the carrier clip right on built onto the die itself. And this one was missing, unfortunately, it was missing a locking mechanism here, which is what this one shows here, that little set screw right there that holds the tube. The set screw goes all the way through, and it's to clamp the tube so it doesn't move as you're bending this. Actually, this goes I think like that. And so all these had, the strap here to carry the tube, but no locking mechanism. So this tends to slip from the tube, when you start bending. So these are actually no good in that respect. So from there, I went on to designing a little. I went on to see online to see how these benders are done in full scale. The more automatic ones, or not automatic, semi-automatic, that are run by motors and gears, at very low speeds by high torque. And so I found a table that had a vise that would adjust the carrier, which is this bar right here. It would adjust via this vise mechanism here. So I did it in miniature, kind of trying to mimic that function there. And so I designed, although these parts are my own design. And if you look at the some of the benders, you'll see there is some differences here, and it's because I like employing my own ideas as I need these things to work, for my particular needs. But a bender is a bender, as long as you get the right characteristics in the bender, you can bend it pretty much in a number of ways. And so this is the locking mechanism here. This is what holds the tube, and this was going to be was what was going to do the bending. So this requires, doing it this way requires a really heavy duty motor. If I were to connect this to underneath via a stem underneath to a motor, it requires a lot of torque because you have no fulcrum, no leverage there on the fulcrum point. And so, but it was worth a try, and this is the reason why I designed this one. As you can see, some of the first ones that I, same concept, they did not have this hex stem here, and the reason I did that hex stem is so that I can put a wrench there, a hex wrench, and try to bend it that way using this as my as the driving force there. So it's very difficult to do it this way, very hard, because you know, unless you have a really long leverage, and this is super strong, this is going to wear out, especially if it's done in just PLA or plastic or ABS even. So it's going to wear out at some point because you're putting a lot of friction there, a lot of force on the stem here. There are better ways to bend than that, but I had to try this because I did see a full scale table that was built the same way. Of course, this is my own setup here with the degrees and with the little pointer here. That's all my, you know, I improvised on that table. I made it in scale, and I wanted to put all these markings here so that I could easily go to 90 degrees on either way. If I would flip this this die over, it would give me the opposite end. And so this is that die that you're seeing there. And you could do that, and you could have both left and right bending. But unfortunately, as you can see, that first one, which was very similar to this kind of with this C bracket here, it broke on this one because I implemented a screw here with a nut, and it was just a weak part. So I decided to make that better, and that's when I went to this setup here with this similar part, but this side is wider here. This whole gripping section is wider, and it's got the set screw on the inside here because I was limited of putting this there as opposed to the other side because of this this adjustable vise that pushes these rollers that creates tension on the back end of this carrier bar here. And so this was my next iteration, and I did bend, you know, with some effort, some pieces. I believe I did this one there, and it worked to some degree, but it started kinking the material there. And I think it's because of my tolerances were not tight enough, and this was because this vise is not really rigid, it's not metal. It was giving, it was flexing a little bit on that side. So I started losing the tension that you need to provide a continuous round curve there. So I decided to start looking at other ways to do this, and I came up with this idea here that I wanted to. The other thing with this is that I didn't have a way to clip this on the vise, and so I came up with this board here that's got that rectangular piece of wood there that I could clamp on a vise, and I could do my bending using this. And so this setup right here was very similar to this, but I improvised with the instead of using those smaller rollers, I went with real rollers here, two skateboard bearings. Of course, it didn't have this plastic part, this plastic curvature, this follower. What would you call this? The other side of the die. It was just the ball bearing, and I was still using the carrier arm right here through there, but it had two ball bearings here, and that kind of worked, but still not quite what I was looking for. So I decided to do away with all that, and decided to just come back and create something that I could mount on a vise directly with using the die. And so this is my one side of the die, and that's why these indentations are there for us, is to clamp it on the vise. So this clamps on the vise, except that this one I did it backwards, and so I reprinted that the right orientation. So as you can see here, this one has that the entry point on towards me, and this one is towards outside, and this is the one that I actually wanted. So you come in with a tube right here. This acts as a stop right there, and I have a certain measurement from here, from this very edge, center line of this hole here, where the pivot point would be, to this edge right here is 1 inch exactly. And so that gives me a good reference to measure from, in case I need to do other bends, and use that as my reference point. So this clamps on the vise correctly, and then this part right here sits right in there, and then this piece right here had this ball bearing set up now with this opposite diode right there, and so that sits in there as the carrier forming diode. And if I can get this in here with one hand, here I'm operating with one hand. Come on, baby. Okay, there we go. And then of course it's got this pin here, and so that sits in there, and that sits in there. And you can see how that when everything's set up, you have those two dies kind of mating each other, and that's what creates the form there without any deformation on the tube. So this worked to some degree, but I was off on the I think I was off on the printing of the particular parts. The first one, this one that I printed on the original one, which was this one right here, started to deform here, and I think it's because I didn't have the right the right amount of the right percentage of infill. So I think I had this at 25%. So on this one, on this yellow one, I went 100%. So every layer is solid on this one. So this is a more solid die. So there's no way that this is going to deform. On this one, I was getting deformation, and I was getting stuff like this. Not a totally curved bend there, but it had a few kinks in the process of that. So I did that one. This one with the 100% infill on the dies should work a lot better, and with a little more closer tolerance between center line to center line between these two right here. On my drawing, on my CAD drawing, these things are butted up against each other, but as when you print, things tend to shrink, especially with plastics and PLA, ABS in particular. You're going to have a little bit of a shrinkage in the parts, so they're not quite touching each other. So this is something that I can adjust in CAD and then reprint these parts. I already reprinted this, and I already reprinted this part right here. So these have a little more tight tolerances. So that die should work in there and provide a nice clean round bend, like on this one right here. See how clean that is? Okay, so I decided that this was a little bit bulky, and yeah, this works on the vise, but I wanted something that works both on the vise as well as on one's hand. And so I came up with this setup right here. And this is just by common sense logic, wanting to do the things that you wanted to do. I start with a requirement. It's like, okay, what do I want this to do? I want this to, have the same features that these other ones proved working. This clamp mechanism here. So I started tweaking the geometry and the design, and I wanted something that I could hold with my hand. Also have a hole through there that I can put a metal bar in and use that as my pry bar in case I want to do this with both hands. And as you can see, use this as a hinge type mechanism that I can do this with both hands, or like I did this bend right here that you will see that the quality of this bend. I clamp this on the vise, and this acts as my stop right there. This has an inch from here to there, so that is my reference point in center line on this edge with the center line of the pivot point here. And it's got the set screw at the back, because since this is not mounted on a table with a vise like that, and it's mounted on a vise like this, just a table vise, it clamps it like that. The side of the vise acts as a stop for this tube right there, and this locks the tube in place as I'm bending this. So that's how I established this bend right here that you see here. You have an inch from the line, from that line right there to the edge right there is an inch. So that's my bend right there. and I already marked this in terms of 1/4 inch increments here, so now I know exactly how much of a bend I'm getting, how much material I will need to add on when I start making real parts. This will come in handy when I make that 1/4 inch or quarter scale go-kart that I mentioned, the Alley Cat. So I just did this bend right here. As you can see, it's very beefy in terms of I wanted this part. I was going to do this part as one piece, that with this carrier die right here, and the bottom is one piece. But I decided, if I print this as one piece, I'm going to have to print it like this, so that I don't have any supports, because I wanted this to, or just print it as separate pieces and clamp it with screws. So this was the better option because it keeps all the parts nice and clean, and I can print this part flat like that horizontally, and these parts also flat horizontally as independent pieces, and so this worked out really, really well. Those screws can be further cleaned up in the geometry of the next part. I can put indentations here to put some hex nuts embedded into this part, so you don't have any screws or anything sticking out. Same thing here, I can indent those, create indentations for the screws to go a little bit deeper there. Maybe use some flathead screws there so that everything's flush. But as it is, it's working really, really well. This is a 1/4 pin. This is a steel pin. I buy these from McMaster-Carr in various diameters to do all kinds of jigs and things that need pins. And so that's just mild steel that you can machine this down if you wanted to, but it's a nice way to attach things really quick. And so this is my better system here. Sometimes the more simple one is the best way to go. And when you start getting complex, when you start doing things like that, this eventually I'm going to do this. I'm going to implement the same features that I implemented here on this one right here, but I'm going to motorize this setup here and put it on a table so that this is all done with a motor. It'll probably be done with a stepper motor using a stepper control, so that I can precisely dial in the angle or the amount of travel, and I can get my angles to whatever degree I want. But this is my latest one, and this is the kind of bend that I got. It's a very nice bend. I'm very happy with that. Of course, this was printed also at 100% infill, so everything is solid here. These parts were aluminum or metal, steel metal. They would even be better because the steel is super hard, and it's great for making dies. But you can also get away with PLA. I've done PLA dies also, not only for 1/4 inch aluminum tubing, but also for steel conduit. And you can see those other videos in my YouTube channel where I talk about creating a dent on 1 inch EMT tubing so that it mates better with the maker pipe connectors. As I was mentioning, this is all done in 1/4 scale, but when I go and do the full scale, I will probably create a similar die to this. Of course, it'll have to be with a much bigger, and I'll probably I'll probably use PLA for some pieces of the die, but also steel is the plate. So these plates will probably have to be done in steel for the full scale die. But this is my die right now. It's a nice little piece. I'm very happy with it, and it can bend from 0 to 90 to full 180 degrees. And when you close it all the way down like that. So this mark that I have right here, just with a marker, as I bent it and I got my 90 degree, I put a little mark there. So I will modify this in the CAD geometry to have a protractor here on this side, and so and maybe put a little just put a little pointer here so that it points to the protractor as I'm bending this, so that I know exactly where I'm at, and I can do any sort of degrees, kind of similar to what I did there, just embedded in smaller scale on this one right here. So that's my bender. It's Mario with MIA Microflight. Once again, stay tuned for more.